We've said before that because God created our system and God created mathematics, and that it is very ordering and makes sense, and that what we've learned in one section can apply to something that we've learned before, and it all works together. It begs the question that says, now that we're learning these combinations and permutations, could this be affected? Could it play into anything else that we've learned in the past? And the answer is yes. Okay, so for combinations, when we are ordering certain items, there's a guy called Pascal, and he said that, let me look at different combinations. And so I've got items, and I'm going to decide how I can take these different items. So if I have no items, then I have a combination of no items taken none at a time. If I had one item, I could choose to either take 0 of those items, or I could take one of them. If I had 2 items, I could choose to take none of them, or I could take one of them, or I could take both of them, and so on and so on. It goes down, and we get this triangle pattern where the first number lines up with the number of items that we had, and then we write out all of the different ways that we could choose to have those items. Always beginning with 0 items and always ending with taking all of them. Now, we know that the order doesn't matter on this, and so there's only one way to take 0 items, which is to take none of them. So every time we had a 0, this is going to turn into a 1. That means at the beginning of this triangle, the numbers are always going to be the number 1. There is also only one way to take all of them, and that's to have all of them. So that means that at the end of the triangle, for each of the categories, we're going to have the number 1. If we worked these out according to the combination formula of n factorial over n minus r factorial, we would get those numbers as well. So what do we get when we have our spaces in the middle? Well, for the first one, I wrote one, we don't have a space in the middle. Sorry, guys. So there we go. What he found was, as we actually worked out these combinations that were in the middle. Let's look at this first one. So a combination of 2 things taken one at a time means we would have 2 factorial over 2 minus 1 gives us 1 factorial, and we're duplicating one time. So we have a 2. If we were to work out 3 things taken at one at a time, we would have 3 over 3 minus 1 gives us 2. We'd have 3 here, and then we would also, when we worked out 3 things taken 2 at a time, we would also have a 3 there. And what Blaise Pascal began to notice was that when he worked out the different ways that you could take these items and started ordering them out, they turned into a very special pattern. And the pattern is that the beginning is 1, the end is 1, and that the spaces between are the sum of the 2 right above it. So if we were looking here, we would have a 1, then we've got 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then we would end with 1. So then for the next row, while we have 1, 2, 3, 4, 5 spaces there, we would have 6 spaces. The first is a 1, the last is a 1. 1 plus 4 is 5, 10, 10, 5, and 1. So he found this and he said, oh, this is an order that when I line up my combinations, I see that this triangle happens. Then once the triangle, which is called Pascal's triangle, happened, there was something where we started investigating binomials. Remember that a binomial is simply two terms that are multiplied together. So let's write out a binomial. We might have x plus 2. That is our binomial. And we have binomials that then are raised to an exponent. It could be squared. We know that this gives us a simple trinomial. It could be raised to the 7th. Oops. It could be raised to the 7th. It can be raised, this binomial can be raised to any power. What ends up happening is that our binomials multiplication plays with our Pascal's triangle. Let's look and erase this and make it generic. Let's do a plus b. If a plus b squared, we know that this comes out to a squared plus 2ab plus b squared. So let's look at the coefficients of each of these terms. We would have the coefficient of 1, 2, and 1. Now, in that case, these happen to match the coefficients of when we had a combination of two items. So the two items tell us that we had two. So we had two binomials, which gives us the list. So our row here of two items. The items just happen to be two binomials, but the coefficients were the number. One of the special things that we learned is when we have something that is cubed, we had a special one, and we said that it was the first one cubed plus 3a squared b plus 3ab squared plus b cubed. So you were asked to memorize that formula, but what does that look like? I now have 3 items. If I have 3 items, I'm going to look at my row for 3 items. My row on Pascal's triangle for 3 items says I have a 1, 3, 3, 1, and my coefficients happen to be 1, 3, 3, 1. So Pascal's triangle is a shortcut way that we can automatically know what the coefficient is for any term in any binomial expansion. And so the first thing is it has to be a binomial. It has to be only 2 terms. And it's raised to a power. The power that our binomial is raised to will then tell us which part of Pascal's triangle we would look at. So if we have any binomial, x plus y, if it was raised to the 7th, we would find the 7th row of Pascal's triangle, and we would use the seventh row where we are a combination of taking 7 things, 0 at a time, 7, 1, 7, 2, 7, 3. And if we didn't know what those were, or if we weren't going all the way out, we could use our combination formula. Because we know that the 7th row means it's a combination of 7 things taken 0, 1, 2, 3, 4, 5, 6, and 7 things at a time. You can't see that there. All right. So as we do that, we also know that when we are expanding out our binomials, that the first term starts at the highest. And so we go from 7 all the way down to 1 for the exponents. And that the second term, so the y's, we go from 7 down to 0, start at 0, and go up to our exponent. So we are able to write a little shortcut formula for a binomial expansion that says when I have these terms, remember, and they're all added up, what do we know about addition? Addition, we could rewrite as a summation. Summation just means to add up a bunch of things, right? We've added up. So I have a summation of my R values from 0 all the way to whatever my exponent is, 0 to 7. Of this first part, we saw our coefficient lined up with our Pascal's triangle. We know that our Pascal's triangle said that I have a combination of maybe 5 things taken 0, 5 taken 1, 5 taken 2, 4, and then 5 taken 5, right? So the numbers that were written in our triangle were based specifically upon working out these combination formulas. So we have a combination of n things taken a certain number at a time, correct? And then that gave us our coefficient. The next term, in this case, would be our x, but it's just whatever our very first term is in here. Typically, they're labeled a and b. So we would have a. So say this would be this is our coefficient. Okay. And then we have a as our first term. The first part of our binomial. And we know that they start at our value, and it goes from that value all the way down. And they're going to keep decreasing. So we write that as n minus r. So the very first one would be 7 minus 0. In this case, if our n value was 7, 7 minus 0 would give us 7. And then we would say our next one would be 1. So it'd be 6. This gives us 7, 6, 5, 4, 3, 2, 1, 0. All the way down there. So we know our a is decreasing. So we have n minus r. And we know that our b value, in this case, our b value is our y. Our b value is just equal to whatever we're choosing the r value at that location. So it matches. Our b value matches the spot that we are in. So it is simply r. So you've got this, what initially looks like a very complicated formula called the binomial theorem. This is what the binomial theorem looks like. But if we break out what it's actually telling us, it's saying that when I multiply out a binomial, so if I take x plus y squared, I know I have x squared plus 2xy plus y squared. Let's do this easy one. That it's saying I'm going to sum up, which I did. I summed up different terms, right? And that each term that I'm summing up, in this case, I'm going from 0 to 2 because my upper value is 2. So I'm looking at the row that says 2 things taken r number at a time, right? So according to Pascal's, I would have 2 things taken 0 at a time, 2 things taken 1 at a time, or 2 things taken 2 at a time. So whichever space, I'm either in the 0 space, the 1 space, or the 2 space. And then I've got, that gives me my coefficient for that term. Then I have my first value is going to be my top one, my n value minus my r value, and my second value is going to be b minus r. So let's see if that plays out. I have a combination. What would my first one be? This would be my r is 0. So 2 things taken 0 at a time. 2 things taken 0 at a time is 2 factorial over 2 minus 0 is 2 factorial. So that gives me a 1. So I'd have a 1. times my a value here is an x. X to the 2 minus 0. 2 minus 0 is 2x squared. And my b value is y. Y to the 0. Anything to the 0 is 1. So those are my three values that give me this first term. 1 times x squared times 1. Well, that's simply x squared. Let's find the second one. The second spot is now my r is equal to 1, right? I'm looking at my second spot. So a combination of two things taken one at a time. I have 2 factorial over 2 minus 1 is 1 factorial with a duplicate of 1 factorial. So that simply gives me 2. So my coefficient is 2. My second option is my x raised to the 2 minus 1. I'm in the 1 section. 2 minus 1 is 1. So it's just raised to the 1. And now my b value is my y raised to, and I'm choosing the 1 spot. We're in the r equals 1. 2xy. Oh, that matches 2xy. What would be y? I now have a combination of two things taken two at a time because I'm choosing now my r value is 2 here. Two things taken two at a time is 1. My x value is now 2 minus 2, which is 0. X to the 0 is simply 1. My y value is now y to my 2, which is y squared. 1 times y squared gives me y squared. And so we worked this out according to FOIL, but according to our binomial theorem, we were also able to get each of the places on it. Now, what this process allows us to do now that we have our binomial theorem in our expansion is we can take any binomial, for example, 5 minus 2a to the 4th, and instead of making this and having to FOIL multiple times, because what this really means is 5 minus 2a, we're going to have 4 binomials here. We would need to FOIL these first two, FOIL those, and then use binomial distribution because we would now have a trinomial times a trinomial. And so we're going to get multiple values. Is instead of working out all of the details there, we can use the process that we know with Pascal's triangle and look over here and say, I'm going to the 4th. I know that whenever I'm raised to the power of 4, it equates with combinations of 4 things taken 0 to 4 at a time. So I'm going to look at my line of Pascal's triangle and say my coefficients already are going to be 1, 4, 6, 4, and 1 when we line them up. Okay? So initially we have that 1, 4, 6, 4, and 1. I could just go ahead and plug them in because I know they have to match. Then my next section is going to be my first value is going to be 5. And 5 is going to be the same all the way down. So this is our logic portion of it. I start with 5. That would be my a value, correct? If we had a, maybe an a plus b is how we talked about it. It starts with 4, so I know I've got to go 4, 3, 2, 1, 0. And then our b value starts as the next part. Our b value in this case is a negative 2a. So we're going to have negative 2a, negative 2a. I know it's a part of every single little section here. I'm sorry, I'm a little cramped. Let's see if we can, let's spread this. There we go. Okay. And I know that my b value starts, the a value starts at your highest number and it goes down to 0. We know our b value or our y's start at the lowest, so we go up. So 0, 1, 2, 3, and 4. And we've been able to write out exactly what we would get if we actually worked out all of the FOILs, the 2 different FOILs and the 2 trinomial distributions for 5 minus 2a to the 4th. And now we have this section here where we've got all of our terms, and then we're going to just simplify. So we have 1 times 5 to the 4th. So we would work out 5 to the 4th, so 25 times 25. We've got negative 2a to the 0, so we know that that just turns into a 1. So for the first one, we would work out 5 to the 4th. For the second one, we would have 4 times 5 times 5 times 5. 25 times 5 is 125. So then we have 4 times 125 times negative 2 times a. And so all of these numbers get simplified. Then we would have all of these values simplified, and it would be a squared, all of these values with a cubed, and then a to the 4th, all of those numbers simplified. So once we multiplied it out, we were able to take our binomial expansion and look at this term, and let's bring this over and see if we can find a certain place. Let's put him down here. Now that we know we have written out all of our terms according to the logic of how we have a coefficient, we have our first term goes exponents from the top down to 0. The second ones go exponents 0 up to your highest exponent. Could we use our binomial theorem and say where would be something where our a value is 2? So they might say something like find the coefficient. That means find our numerical value when our a value is 2. So we are looking for, in this case, the red ones are our a values. When our a value is 2, what are the numbers in front? And it says we used the combination. Here, it would be 4 things taken how many at a time? To get to the value where it's 2, we need this exponent to be equal to 2. So if my n value was 4, what does my r value have to be to get it to be 2? So n is 4, which means r has to be 2. So we are looking at our r value of 2. That means we're also going to plug in b as our r value is 2. So it's automatically telling us that our b value is going to be squared. And we see that is the case, that our b value is also squared. Here's a note. Your exponents will always add up to be your original exponent. So as you move down, you need to make sure that they always add up to be that original exponent, which also means that your exponents here are going to add up to be your original exponent. So if we're looking for the a value of 3, that means our b value had to be 1. So our r has to be 1. That's another way that we can quickly find what our r value is. So yes, we're able to use our summation formula to find any coefficient. So let's work a problem that we've got. Here, I'm going to leave my Pascal's triangle up there. And let's see. It says, let's do number 33. So it gives us x minus 3y to the 6th. And it says use Pascal's triangle to write out the binomial expansion. So if I have the exponent of 6, that means I need to find the combination of 6 things taken 0, 1, 2, 3. So we know that it's going to be 6 is our first one. So we need to finish writing up 6. We've got 6, 15, 20, 15, 6, and 1. So these are our coefficients. So if we were writing out our terms, we would have 1, 6, 15, 20, 15, 6, and 1. Those are going to be our sections for our coefficients. Then x, this is our a value. B is our negative 3y. So we take our a values, x, we're going to plug them in. And our x values start at 0 and go, start at 6 and go all the way down to 0. So we go 6, 5, 4, 3, 2, 1, 0. Then we're going to plug in our b values and have negative 3y, negative 3y. And I'm not putting signs between here in the first place. You could always do an addition sign. But as we work out our numbers, it will tell us what the sign of that term is. But just remember that these are all little separate terms and that they are going to have some either addition or subtraction in between each one of these term spaces. So we're looking at little individual spots. And our b value starts at 0 and works its way up. 1, 2, 3, 4, 5, 6. So this would be our binomial expansion that is written out, but we would need to actually simplify what our values are. This one raised to a 0 is going to be 1, that goes away. This one to 0 is 1, goes away. In this case, we have 6x, or 1 times x to the 6th. Then we have 6 times x to the 5th times negative 3 to the 1st. So now we're having to use our exponent rules. It gets distributed. Negative 3. So negative 3 times 6 is negative 18. X to the 5th y is what's left there. Now we have 15. X to the 4th. Negative 3 squared is 9. So you would have 9 times 15. And that's going to give us, let me see what we have. 135, x to the 4th, y squared, and so on. So in this case, we've got 20 times a negative 27 gives us a negative 540, x cubed, y cubed. And we're going to move down to write out our binomial expansion. Okay. Using the theorem itself, where what we really did was just sum up from 0 to an n, our combination of n things taken r at a time, our a value of n minus r, our b value of r. This is starting at the top, moving all the way down. This is starting at the bottom, moving all the way, starting at 0, moving all the way up. We can solve questions that say, find, let me see, which ones? Let me look and see which one it says. Like 44, 45, and 46. 44 says, find the coefficient. They're going to give you the binomial. The binomial is x minus 3 to the 7th. And it says, find the coefficient of the term that has x to the 5th. So first off, when we look, we've got x to the 7th, which means we have our 7th term. So we need our extra row down here. We need 1, 7, 6 plus 15 is 21, 35, 35, 21, 7, and 1. So here's the row we're going to use. Okay. We want to find which of these terms would have x to the 5th. Well, we know that our x is our first value, and it starts at the top. So we would start with 7, 6, 5. So our term, the 7, 6, 5, would be 21. So it should come out that the very first spot that we have would be 21. That's going to be this section. So does that work out that way? If I take a combination of 7 things, what would my R value need to be for my X value here to be 5? If I want this to equal 5, I know N is 7. 7 minus what equals 5? We also know that my exponent for the first one and my exponent for the second one, these have to add up to equal 7. So if this one is 7, if this one is 5, if my A value I'm looking for is 5, then my B value has to be what for these to equal 7? My B value has to be 2. So we are looking for an R value of 2. So I would have a combination of 7 things taken 2 at a time. We can also see from our Pascals that it was 0, 0 at a time, 1 at a time, 2 at a time. So that's right, 7 things taken 2 at a time. 7 factorial over 5 factorial, 2 factorial gives us 7 times 6 over 2. These cancel, and I really have 7 times 3 is 21. So yes, indeed, our coefficient is 21 for this one. So this gives us our coefficient part. Now, our A part, we know A is X, so it's going to be X. N minus R, we already said we wanted it to be 5. We're doing 7 minus 2, so that's 5. Then our last section is our B. Our B is this entire -3. The sign goes with it. So we have -3 to what? Our R is 2. So when we break it up, we have been able to find that all parts of the term where X is raised to the 5th include a coefficient of 21, an A value of X to the 5th, and a B value of -3 squared. So what we indeed have is 21 times 9 times X to the 5th. And 21 times 9 is 189, X to the 5th. So the coefficient of that term is 189. We were able to combine this. So if we were to put 7 of these out, multiply them all out, combine all of our terms, we would end up with a row with 1, 2, 3, 4, 5, 6, 7, 8 terms. Remember, we always have one more term than what our exponent says. So we would have 8 terms because we had an exponent of 7. And when we found the terms that had X to the 5th, the number in front of it would be 189. So that's how to use our binomial theorem. Why it works that way, the different little spaces. I wanted you to see that it's not really one big random long formula, that the combination gives us our coefficient. The A values give us the first term and its exponents. The B values give us the second part of that term, the second part for our binomial there. And if it happens to be a number or have a number with it, then we work those numbers out as well.